Yeah, hello everybody. First of all, I organized for the presentations that we will go to the youth hostel in Jever on the 15th, 16th of December, and you will get then further information. Okay, we had some exercises left, especially now looking again on data, and yeah, one little example, I think it is not that hard to do it, that we have some values for x, 0, 1, 2, and 3, and the number of counts of the data is that we have 10 times chosen 0, 20 times 1, 50 times 2, and 20 times the number 3. What should we do? Calculate median, arithmetic mean, unbiased variance, unbiased standard deviation, skewness, and kurtosis. Yeah, again, let's cut this. And I think we should also do this in Excel, but first of all this and this. And then so this is then A6, and data was 10, 20, 50, 20. You see this? Yep. 10, 20, 50, 20, and 0, 1, 2, 3. This were X, and this were the counts. Yeah, well, we could maybe also at first we can have just a look and look at it graphically in a histogram. So this X we don't want here, but we want to have X here. Until G or okay. Yep. So smaller. Oops. There's 1, 2, 3 not here. Data. This should be B3 until this one. Okay. Oops. So, so this is how our data looks like. And then first of all, what is the median of this distribution? If you look at the data, so maybe the sum of all counts is 100. So where do we find then the median of this distribution? The median again cuts our distribution in two parts. 50% of the data is lower and 50% of the data is higher than our value. Yep. Yes. Yep. 20. Well, you have here x. Oh, so we have what the numbers for our variable is 0, 1, 2, and 3. And please do not mix this up with the counts here. So we have 10 times chosen. Maybe you can say that it is throwing or taking just out of some class that you have chosen 10 times the number 0 and 20 times the number 1. So I have a data set of 100 pieces of paper maybe, and these pieces of paper show 10 times the number 0, 20 times the number 1, and 50 times the number 2, and 30 times the number 3. So I have 100. So then I sum up from the left 10, 20, and plus 50 is 80. So the 50 largest number we have is the number 2. Okay? And the 51s is also the number 2. So what you, so to speak, have is that we have 10 times. So let's start here. Until 100. No, sorry. Plus 1. We're already 100 here. Almost. So how does our data looks like? Our data looks like when I put the data in a row that we have 10 times 0. Then we have 20 times 1. Until 30. Then we have 50 times number 2. This is until 80. And the last 20 is 3. So, and what we then are looking for is here the number 50 and 51 and taking the arithmetic mean. But the 50's largest and the 51's largest are the same number. And therefore, of course, we then obtain just 2 for the median. and don't mix it up with the number of counts. Okay? So here we have the median. So the median is just 2. So then the arithmetic mean. What do we have to do here? Well, somehow in this table our data is more or less already sorted. We could now take here the arithmetic mean from this 100, or for example, let's do it. So we could use the formula and then we obtain 1.8, or we can directly calculate it. So we have 10 times 0, so 10 times 0 plus 20 times 1 plus 50 times 2 plus 20 times 3, and this has to be divided through the number of the whole data set, so divided by 100. And hopefully we will obtain the same number. So what else should we calculate? Unbiased variance and unbiased standard deviation and skewness. So for this, we then need the squared distances of all our data points, and we need the distances up to the power of 3 and to the power of 4. Then let's move this upward and this just downward. And maybe this looks then also better if we take this. So the distance of 0 with respect to the arithmetic mean. When we take here, let's put it like this, squared distance to the power of 3 and to the power of 4. Oh, sorry. Then take here x minus x bar. Let's put it also in here and in here. So this would be then 0 minus 1.8 squared, and this we have to do for 1, 2, and 3, always with respect to x bar, so we fix this with two dollar signs. And then we need the distances with the power of 3, so we should stay at 1. Then we have also to put a dollar here, and let's copy this again, because now I can just move downward everything, and I only have to change here the power. This is with string h, and then I change the power of 2 into the power of 3. And for the kurtosis, I later on need the power of 4. And this we change to. This is then from 3 to 4. Okay, and now we need, of course, for the unbiased variance. Did you still see? I need some space here. Let's move this a little bit down. So the variance is then 10 times the squared distance of 0 with respect to the arithmetic mean. So equals 10 times 3.2 plus 20 times 0.64 plus 50 times 0.04 plus 20 times 1.44. Unbiased means divided by n minus 1. So over 100 minus 1. This would be then the variance. Click in here, yeah, this times this, this times this, this times this, and so on. So then the standard deviation is just the square root of this. And now we need the skewness. And the skewness, if we look up our definition, standard deviation, skewness is the sum of the distances with power to 3 over the standard deviation to the power of 3 divided by 1 over n. So for this we then need 10 times minus 5 plus 20 times minus 0.5 plus 50 times 0.08 plus 20 times 1.72 divided by the standard deviation to the power of 3 and divided by the number of our data set, so the 100. And this is a skewness of roughly minus 0.5. And if we look at the distribution, then this is also okay, because here on the left side we have a little bit more data, and our arithmetic mean is also, oops, why is it here, the 0.8? I think this is because I copied something in a wrong way. This is not B, but this has to be 1. So here at 1.8 we have the arithmetic mean in our distribution, and then we see that it is skewed a little bit to the left, and therefore the skewness has to be with a minus sign, because only in the symmetric case we would have a skewness of 0. And the kurtosis, this is then again 10 times this plus 20 times 0.4 plus 50 times 0.06 plus 20 times this, and I need brackets again, and now divided by standard deviation to the power of 4, again divided by 100. And kurtosis of 2.6, and there is a kurtosis. So here we are looking at the benchmark, so to speak, of a kurtosis of 3. This would mean that we are quite close to the normal distribution. Well, and also if we have a look at this, this looks like then also more or less like a broad normal distribution. So we are also not very surprised that we here quite close to a kurtosis of 3. Okay, so then let's put all this number into the slides. And also all this. And also, of course, later on I will upload the Excel file for you. So, then last week, I was quite surprised that I couldn't find any more the data for the DAX development at the statistics part of the Bundesbank. I looked it up the last day, so it's really gone. Maybe there are some problems that the German stock market said that you are not allowed anymore to put the data. So time series of the DAX is not anymore available at the Bundesbank, or I couldn't find it and I really tried it. So Then, yeah, I used some other open source because I don't want to pay for it. If you go to the German stock market, then you have to pay for an account to get directly the data. But in the internet, you quite often find also free data and open source data, for example, at Google Finance. So, and how to download it in a sophisticated way, this I also had to learn. So I will just show it to you, and maybe this is also helpful if you are interested in time series, then Google Finance is a good source. So at first, of course, you need an account. So I created some new account for me, and then maybe you already know this. You have the cloud service of Google, and you have, I think, a 15 gigabyte in order to use it. And then you can open a spreadsheet within the cloud. Well, and then comes the harder part, because now you have to know the syntax, how to get the data. And where do I have it? I think here. So there, of course, you find tutorials in the internet. And so the first part here is just the name for the time series you want to. Price means just that you want to have the stock market prices, and this is then the date. But also you have to be careful if you use the German version or the English version, because in the English version the commata and the semicolons interchanges and so on. So it is a bit tricky, but you find many tutorials. And well, if you are interested in finance data and you don't want to pay for it, then Google Finance or Yahoo Finance or so is really a good choice. But of course, as always, you have to try it, and you have to use it quite often, because otherwise you are always again looking how is the syntax. Well, oops, what did I make wrong now? Anything is wrong? Let's copy it again. Maybe I lost some bracket. Enter. Now it seems to work. Yep. So, and this is then our data, and with this data I want to go again to Excel with you. I will not do all the manipulation with you right now, because this would take too long, but yeah, this is how I did it. I just put the data into one Excel file, and then of course we can look at the development. So this is then the DAX performance over the last roughly 30 to 40 years. And yeah, what I wanted to do with you now is to calculate the skewness and the kurtosis and interpret this. So at first, maybe we can just put the DAX development. Well, and what we are interested in is, of course, the yield. If you invest in an investment fund, which is rebuilding the DAX, then you're of course interested in the yield. And let's calculate for this now. At the Bundesbank, we had monthly data, and now we are calculating just the daily yield of the DAX. Daily yield. This would be just the growth rate. So the value divided by the former value minus 1. And in order to have it not in percentage, I multiply this with 100. Oops. Oh, sorry. Now, in order to just I have to, what do I have to do? I think this one here. Up. Because now I can just jump to the end of the time series. For this, I made this. Then let's also look at the DAX yield distribution over time. Where we are, yeah, this is okay. So then and here you see then, of course, this is a movement upward and downward over the last 35 years. And we also have to change, I think, the description of the axis. Do we have here? Oh, this you don't see. Sorry. So this is the daily yield, and you see. Oops. A little bit puzzled because of this description of the vertical axis, because here we should find these numbers. Then let's try it in another way. So put in the yield and the data. Okay, and on the horizontal axis, the dates. Why is this? I don't know. Maybe this is formatted in the wrong way. No, it's okay. Yeah. So the format was just in date, and therefore I got here the wrong description. So this is now in percentage. Mm. This is the DAX daily yield. DAX daily yield. So, well, and then I may be interested in the distribution of these yields. And for this, I created for you some histogram. So then I counted all times during the last 35 years when the yield was less than, so this would be yield, less than minus 12.5%. So how often does it happen? Did it happen the last 35 years that in the change from one day to the other day, the drop down of the DAX was more than 12.5%. And then, fortunately, this didn't happen quite often. It happened only once. And then in between 11.875% and 12.5% downturn. This happened also only once. And this would be then the next interval. There we have a count of 0. And if we go then in the neighborhood of a change nearby 0%, because, well, a time series of such an index, we do not expect that we have quite often very high changes in in the year in the daily yield. So from one day to the other day, maybe it's 0.5% or something like this. And if we go here more on the right, then we have here the 0, and then you see more or less that around these small changes plus minus we have the most counts, of course. And this I plotted then, and so we see then just by eye it's a more or less symmetric distribution around the yield of 0%. so with no change from one day to the other day. Well, and then we can now be interested in the kurtosis and in the skewness. So is there maybe a bias to slightly below or slightly higher than 0% during the last years? And the kurtosis, where did I calculate this? Here, skewness and kurtosis. And then we see, well, that this is quite close to 0. And so we see that we have a highly symmetric distribution of the DAX performance over the last 30 to 40 years. Well, this is also not very surprising since, yeah, we think that at the stock market, in the theoretical way, we say that this is more or less a perfect market. Every information in the world we see within the stock market, we see within the price of the DAX, and therefore the first assumption is that the yield of the DAX is just a random walk. That with 50% probability it goes up, and with other 50% it goes down. Close to 0, so the DAX development is highly symmetric with ups and downs in the daily yield. Well, but what we now find is really interesting, that we had a kurtosis of 9.5. And this means this is much larger than 3. And how can we interpret this now? So the general assumption of a random walk would be that the DAX yield is also distributed like the normal distribution. But the normal distribution has a kurtosis of 3. So also this is much larger than the kurtosis of the normal distribution. And how can we interpret this? That we have much more outliers than we would expect if we assume that the stock market performance would be like a normal distribution. So let's write it down here. This can be interpreted that the DAX yield has much more outliers compared to the assumption of the normal distribution. And this means within the distribution we have these so-called fat tails. So um, no, I do not have any space left. Then let's write it down here. So financial data has quite often fat tails in the distribution. Yeah, and this is what we really find quite often. On the other hand, we still quite often use the normal distribution in order to describe also financial data. I don't know, have you already heard of the so-called Black-Scholes formula in order to price options in financial markets? No? So this is yeah, one of the standard ways, and there behind is at the starting point that the ups and downs at the stock market follow a normal distribution. And then we have to admit, okay, if we use at the real data, then the outliers will happen much more often than it would be due to the assumption of a normal distribution. Okay, and yeah, one last anecdotal example that we also have to be careful when we interpret the kurtosis, what I right now did, that a kurtosis larger than 3 would mean that we have more outliers. So if you look at a distribution like this, so again, as in the example number 6 on the exercise, x can be the number 5, 10, and 15. And in the first distribution, we have 30 times the number 5, 0 times the number 10, and 30 times the number 15. Okay? And for this, yeah, let's just look. I think I had it already here, but I will do this together with you. For this, we can also just look how these distribution look like. So the first one would be then this one, and again, we want only the counts, and for this we want the x values. So this would be then the first distribution. Let's put it here. So maybe more, so we can then put it just under this one. So the next one, let's copy this. There we have to change from C to D. Data. D. This would look like this. "25" would mean everything has the same. So this would be then E. E and E. This is just then a uniform distribution. And then F. And the last one, G. So, and if we now would interpret the kurtosis as that you have many outliers. So which distribution here from a graphic standpoint you would think that you have a distribution with many outliers? What would you think? Just by looking at it without calculating it. So what distribution more or less looks more than a normal distribution, and which would, by just having a look at it, looks like that it is really spread and has many outliers. What do you think? Yep. Yeah. Yes. No? Yeah. Yeah. So you are right. So if we just have in mind that kurtosis of 3 would be that we are quite close to a normal distribution, and we interpret this as that we have many outliers, then maybe we would just say that this would be somehow a distribution with many outliers. Well, if you see it here, I constructed it that always all of these distributions are symmetric. So of course, then we have a skewness of 0, and the arithmetic mean is always 10 because we are symmetrically distributed around 10. Well, and the surprising thing is that if we now calculate, and this I did here for you, the kurtosis, that it is just the other way around. So, it's too much. So kurtosis, all right. So well, if we say this would be 1, 2, 3, 4, and 5, if we look at the graphic or the representation, oh shit, I didn't start the recording, I see, or? No, I did start it, okay. Whew. If we look at the graphic representation of the distributions, we would think that 1 is a distribution with many outliers and 5 with only little outliers. But calculating the kurtosis it is just the other way around, because here we have this kurtosis of 12, which is much greater than 3, and here we have 0.1, which is much smaller than 3. Well, and the reason is, if we look at the formula of the kurtosis, then we see here, maybe I should just take this formula here. That we, when we calculate the kurtosis, we normalize the the distance with respect to the arithmetic mean by the standard deviation with the power to the power of 4. Well, the reason is that the kurtosis is normalized with the standard deviation. Well, and now if we look at the distribution number 5, then we see that we have a really, really narrow distribution. So the standard deviation of this distribution number 5, I think I also calculated it. Here, the standard deviation. Let's put this also in here. Then we see that number 5 is a very narrow distribution with sigma hat equals 1.38. So, and here we are distributed from 5 over 10 to 15. And one standard deviation is only 10 plus minus 1.3. So, although we have only one outlier at 10 and one outlier at 15, compared to the mean of 10, this has a distance of 3 times or more than 3 times the standard deviation. So because this distribution is very narrow, these 2 points, although it's only 2 points at 15 and at 5, they are really, really far away from the arithmetic mean of this distribution. And therefore, it counts really hard that we have these far away lying data points. Well, and here we have at distribution 1, we have a very broad distribution with sigma hat roughly 5. So although in the middle we have no data point, these counts at 5 and 15 are still within one standard deviation. And therefore, although we have no data point in the middle, we have all our data within an interval of one standard deviation. And therefore, these data points, yeah, roughly spoken, do not count as outliers because they are still within one standard deviation. And here, these count really hard as outliers because they are outside 3 times the standard deviation. And yeah, usually we also say that you just only start to do statistics when some data point is really within 3 standard deviations. And why I did this is also that you always have to be careful when you interpret your numbers. And here you have to interpret this the parameter of kurtosis also in a relative way, and not only just look at the data and say, well, this is the distribution with the outliers. Okay, without the outliers, because it's only 2 data points, but they really count hard. Yeah. Then I'm now done with my introduction and yeah, some new parameters, especially kurtosis and skewness, and yeah, especially people who are interested in finance, they will I think, quite often find also these parameters and not only the variance. Yeah, then we stop here for today, and the next time or tomorrow then we start also with the linear regression. The guys who are hearing also global economics, you have already heard this. I will use a little bit more time in the statistics course, but yeah, then tomorrow we start with the linear regression. So thank you very much for today and see you tomorrow.